Hello and welcome to the lesson on momentum and impulse. So today, what's our goal? By the end of this, I want you to be able to explain in your own words what is momentum, what is impulse, and then apply them to some real-world problems that we're going to see in the homework. So momentum, let's talk about it in your own terms. So usually, I always kind of start off the class by asking what in your mind is momentum, and some of the more common answers I've gotten in the past is gaining speed. So an object is gaining speed. I've also had people tell me that it's objects moving without force, without applied force. So they're talking about the momentum of an object will keep it moving. It doesn't need that applied force anymore. So all kind of around the right idea, I suppose. But really, it was coined as, and Newton coined it as, a quantity of motion. All right, and that's how we're going to leave that definition as to what is momentum. Well, it's a quantity of motion. We're coming up with a calculation that relates our mass and our velocity, because the above terms are kind of correct. So momentum is a vector. So make sure you add the vector notation on your note. And it is our mass times velocity. So what is our units for momentum? So our units, mass is measured in kilograms, velocity is meters per second. So kilogram meters per second is the units for our momentum. All right, so the formula is not overly complicated as you're taking a look here. So momentum is our p-value, momentum, m, mass of object, and v is velocity of object. So relatively simple formula, and that again, that'll calculate our quantity of motion. So let's move on for a second and talk about, just in general, what has more momentum? A slow-moving car or a fast-moving truck? Okay. Well, what do we know about the car and the truck? Well, we got to make some assumptions here. So what am I going to assume? Well, I'm going to assume that the mass of a truck is much greater than the mass of your average car. So I'm making that assumption. So then when we look at our velocity then, it's stated here that we have a slow-moving car, so that means the velocity of the truck will also have to be greater than, or is greater than, velocity of the car. So therefore, if that's true, mass of truck multiplied by velocity of truck has to be greater than mass of car, velocity of car, from those two algebraic statements. What happens if we take that same car and truck that's traveling at the same velocity? Well, again, we're going to make that assumption on the mass. So I'm still going to say the truck's mass is greater than the mass of the car, but now our velocities are now equal. So does that change the statement? Well, mathematically, most of you will be saying no. It's still true that the momentum for that truck is still going to be greater than that of the car, and that's simply because of this inequality right here. Okay. So finally, what happens if the car starts moving very, very fast, or faster than the truck? So assume, same thing, we're still saying the mass of the truck greater than mass of car, but now we know that the velocity of the truck is smaller than velocity of car. So when we go to take the product of the two, mass of truck, velocity of truck, mass of car, velocity of car, well, it's going to depend. It's really going to depend on what that ratio is between the change in velocity and the mass. So we need to know more information. However, it is possible that the car's momentum is now greater than the momentum of the truck, depending on its velocity. So there is that potential that you don't necessarily have to be the biggest object to have the most momentum. So moving on to a couple of quick examples here. What is the momentum of the 1,000 kilogram car traveling at 80 kilometers an hour west? So just listing my information quickly here. 1,000 kilograms. Velocity is 80 kilometers an hour. Remember, we need to work in our SI. We need to get that to meters per second. 22 meters per second, and that is still west. That's all the information we need. So momentum equals mass times velocity. 1,000 multiplied by 22.2 gives us 2,200 kilogram meters per second. And yes, you do need the units. And yes, momentum is a vector, so we do need our direction. All right, and then you write out your therefore statement. So there is the momentum of a 1,000 kilogram car moving at 80 kilometers an hour. Next example, very, very similar. All I can really do, there's only 3 terms in the equation, so I'm just going to give you a gist of what's involved here. So velocity of bullet, VB, is 900 meters per second west. We know the momentum, it's given, 4.5 kilogram meters per second, also west, which is a good thing. Find the mass. So, I mean, I'm asking grade 12 students to take a 3-term or a simple equation and solve for an unknown. 4.5 equals m times the 900. Mass of bullet then, when we do the division, would be 5 times 10 to the negative 3, or that's what most calculators will give, which transforms or can be converted to a 5-gram bullet. Then you would write up the appropriate therefore statement. So you can see the calculations are not overly intense at this point in time. So we're going to take momentum, we're going to take it a step farther, kind of in the next lesson. However, this is just the introductory material. So now we're going to move on to the second term that was listed in our title. So we're doing momentum and impulse. And momentum and impulse is somewhat related, or it is actually related. And what impulse is the amount of force applied over a period of time. So if you play a sport like baseball or golf, you always hear the term, or you often hear the term follow through or contact time. Well, that's what people are really talking about. They're talking about the impulse, because we're talking about the amount of force applied over a period of time. Impulse is capital J. All right, so that is the term for impulse, and it is your average force multiplied by the amount of time it's in contact. So J is your impulse. F average is your average applied force. Average applied force. And delta T is your interaction time or contact time. All right, and when we look at the units, I'll do that underneath in here. So what are my units? My unit? Wow, spelling, what can you do? Units. So force is measured in newtons, and we're multiplying by time, which is in seconds. So impulse is Newton seconds. All right. I can make a Star Trek joke about impulse, but not very many people would get it. Make fun of me the next day anyway. So impulse is also equal to, or known as, our change in momentum. So our formula, we can adjust our formula and give you a different format for the formula, so it really depends on the information given. So if impulse is known as the change in momentum, that means it will be J equals delta P. Delta P is momentum 2 minus momentum 1. And I'm going to make a bit of a circular argument here. So that's what J is equal to. Now J from above is F average multiplied by delta T. It's equal to momentum 2 minus momentum 1. And to complete the circular argument here, force average multiplied by time is equal to the change in momentum. So most people don't bother writing out all 4 formulas. Some people write them all out on their study sheet. It doesn't really matter, but they are related in those kind of variety of ways. All right, so it's just a matter of decoding what information do I want, and we move from there. So An example, a baseball, mass 0.152 kilograms, is traveling 37.5 meters per second east, collides with a baseball. Baseball, it collides with another baseball. This collision lasts for 1.15 milliseconds. Immediately after the collision, baseball is traveling 49.5 meters per second west. I'm going to say it should say baseball bat to make it a little bit more realistic. So we're looking at a baseball being struck and returning back. So the pitch comes in. So A, what's the initial momentum of the ball? So the momentum of the ball is equal to mass of ball multiplied by velocity of ball. So 0.152, it's nice, it's already in the right units, multiplied by 37.5 will tell us the initial momentum of the ball, kilogram meters per second, and it is heading east. So no appropriate therefore statement can then be put in there. So that's the ball before it struck the bat. B part. What's the final momentum of the ball? So we're still calculating the ball. So this is going to be final. So you can put F and I. So maybe I'll go back and put PBI for initial, or you can put PB1, PB2. Doesn't really matter. It's whichever you prefer. So again, the mass 0.152. Velocity is now 49.5 meters per second west. So when we do that calculation, we get 7.5 kilogram meters per second. Now it's heading west. All right, and then you can copy in or write in the appropriate therefore statement. So what's the average force applied by the bat to the ball? Okay, so we're looking for average force. We do have a formula that has average force, so C part, and we know that force average multiplied by delta T is equal to impulse, but I don't really have an impulse here. A and B, though, has given me an initial momentum and a final momentum, so technically I know the change in momentum. All right, so I'm going to find average force applied by the bat using this particular formula. So FAV, that's my unknown, is equal to contact time. So 1.15 milliseconds. We've got to be careful here. So milli means that it's like millimeters. Okay, you got to divide that by 1,000. So it's actually 0.115, sorry, equals final momentum minus initial momentum. So as we calculate and isolate here, we end up with, oops, I got to be careful here on my directions as well. It is the change momentum, so don't have to erase it. I just need a little bit more space for me, so you don't have to erase that line. If I'm going to assume east is positive here, so again, if I go back to my directions that are positive, east and north are positive, that means that 7.5, because it's heading west, it's got to be a negative. It's a vector. Minus, now the 5.7, the answer from A part is heading east, so it is positive. So we've got to be very aware of our signs here. So we need to be very, very careful when we're doing those calculations. Okay. So doing that calculation, we subtract those together. So that gives us negative 13.2 divided by 0.00115. When you do that division, you end up with negative 11,478 newtons. And it's negative, so I will say initially it is east. When I do my therefore the force is 11,478 newtons west, which makes sense since that's the direction the ball is traveling at now. So I got a couple more examples I want to go through, and I'll finish that up in the next video.